Let's start again. Thank you everybody for being here. It's an unusual Friday because we have the NCAA whatever tournament right now. But thanks all for coming. It's my pleasure to introduce somebody that needs absolutely no introduction. So I'm not going to introduce him anyway because all of you know him from afar, from close, and for a long time. So Jose Castillo, or director from the CSRC. And he's going to be talking about something that he has been brewing for a while. He's been working on this topic for many years. He's considered a worldwide expert. Actually, he was the creator of this type of operators, the mimetic operators. He's going to be talking about this library that I have built so that we can tackle many different problems. And I'm just going to mention, I don't know if you're going to say something about the acronym. I'm here because of the mole. So if you're not Mexican and you don't know what I'm talking about, it's the most delicious Mexican food that you can ever taste. Mole. I really recommend after hearing this talk, even if you get into mimetic operators or not, to actually go and get some mole. So maybe you can get the mole with mole, but it's going to be nice. So thanks a lot, Jose, for sharing your work.
Who is he again?
I don't know. It's a guy that I
and also has nothing to do with chemistry.
Yeah.
Although it could be the library using
Eureka.
Okay. Well, thank you, Ricardo. Today, I have talked about mimetic methods before, but we actually have developed this library, which is a way to facilitate the use of these operators. Okay? That's the main goal. Basically, what is more? It's a high quality C++. We have two versions, C++ and MATLAB version. And the reason we created a MATLAB version is because everybody uses MATLAB. But basically, the kernel is C++. We discovered that we actually are very close to have an octave version because we don't use any function from toolboxes. So in Prism, we will have an octave for people outside the MATLAB license. Okay, but basically, the way that I introduce in the library now is a building block to construct high performance codes using mimetic operators. That's, I think, a way because we actually, the idea of mol, it only gives you divergence, gradient, and curl. That's basically what it produces for you on a staggered mesh. But mostly all the equations in mathematical physics can be written as in terms of the first order invariant operators that vary divergence, gradient, and curl. So standard people in, let's say, finite difference, you approximate the derivative, and then you have basically discretize the equation, and then you solve at the end a linear or nonlinear problem, depends on the nature of the problem. Finite elements, you represent the solution, you assume the resolution can be represented as a linear combination of some basic functions, and then you use those to discretize the equation. The philosophy in what we call mimetic method is totally different. So we actually don't discretize the equation. What we do is we construct discrete operators, divergence, gradient, and curl. And these discrete operators, they satisfy, they're called mimetic because they mimic the properties of the continuum operators. And they satisfy, in the discrete sense, the same properties that the continuum operators do. So another way to put it, we're talking about building a discrete vector calculus, but on staggered meshes. The standard vector calculus is in nodal grids. So this is an equivalent, but in staggered meshes. And we know, we have many people found out that staggered mesh is the right mesh to solve physical problems. For example, this is a, we have a map here. Okay, basically, we do have, at least when I went to school, they talk about, they put a little square, and they said there is something coming this way, going out this way, and such and so. But where is it coming? It's coming in the edge. It's not coming on the nodes, but when you use finite differences, then basically the approximation we're doing on the nodes. And in 2D, we're in the vertices. Well, if you use that approximation, and let's say you're solving a hyperbolic problem, a wave equation problem, you will end up with Gauss spurious modes, and the solution will not be faithful to the physics. Not only that, you cannot even prove convergence. So it's in the edge, because we are told it comes here, and in the limit, it collapses to the center. So this becomes a point right here. So which is more natural for staggered measures. Okay. So what is our goal? This is very old from the beginning. Basically, everybody who works in developing numerical methods for solving PDEs, they want the same. They want to be able to produce solutions which are faithful to the physics. Conservation is one important thing, conservation laws. So we want to construct local, that means that you only use the neighbor points for the in your stencils. So high order, which is usually more than 3, divergence, gradient, and curve operators on uniform and non-uniform grids that they mimic symmetry properties of continuum differential operators. Okay? Now, these operators that we do, they're basically are discrete analogs, as I mentioned before, the continuum operator. They satisfy vector calculus identity, satisfy global and local conservation laws, and provide uniform order of accuracy up to 8th order. And this is unique. Okay, there is no other method published anywhere that achieves the same order of approximation in the interior as well as the top. And that's actually very important. It looks innocent, but it is important, because if you're doing a problem where you have to compute in the flux, that means the gradient that you're using has a higher order than the old standard method, and that makes a big.
Yeah, so there's no other method. What about if I just use finite differencing? I can define the order anywhere.
Yes, but they don't satisfy the property that I'm talking about. Okay? I'm talking about methods that satisfy all these properties, and they also have the same order of accuracy. And it's natural. When I construct this, I don't have to come up with anything. In finite difference, you approximate here, and then in the boundary you have to invent something, which is not germane to the method. Here, I construct the operator, and when I derive the scheme, the boundary is incorporated. I don't have to do anything else.
Are you going to talk about how you actually deal with boundaries, or that's not part of the talk right now?
I think it's mentioned there, but it's actually very easy. Okay, so this is one of the standard properties that we want them to satisfy. So the gradient of a constant is 0. You're going to tell me, well, finite difference do that? No, actually, I can give you an example, very easy, with an oscillating function where the derivative of the function is 0, but the function is not constant. That's very easy, very example. If you're talking about a problem which is second order, that's maybe not that harmful. But if you're talking about a problem where it has a, how do you call it, more difficult, let's say, and there non-linearity or something in long term, that is something that will play an important role in the PDE. So it's called the free stream preservation. You got the divergence of this vector to be 0. The curl of the gradient is 0. The divergence of the curl is 0. And the divergence of the gradient, if we do this, we obtain the Laplacian. If you find a difference, you can write an approximation to the Laplacian, works very well. You can decompose that into operators, into the divergence of the gradient. You can, if you construct find a different matrix representation, you can do that, but it won't satisfy those properties. And you can also don't decompose it.
I think that the key here that you mentioned, just want to stress it if I understand correctly, it is not that you're discretizing your equations, it's that you are formally rewriting your problem using
These operators.
these operators.
Yeah.
So you're I mean, you're not solving the actual problem because you're in the end you're going to be discretized somewhere, but you're exactly solving a discrete version of the original physical problem.
Well, it's a discrete analog of the original equation, which nobody solved directly.
Well, nobody can solve it directly. We use computers that are discrete, but yeah. So that basically the essence, right?
That's one of them. And the main thing that is also an important aspect, yes.
So in this case, is Laplacian not defined in terms of the divergence of the gradient?
Yes, that's what I said. That's
Well, you have this equation down there, but if EG is equal to L, I mean, equal to L.
Yeah.
the operator.
well, I can delete the L if you the F that bothers you. I'm just trying to say here that if you take the divergence and the gradient, you get the Laplacian, which just doesn't happen in finite difference.
Sorry,
So here is one of the main important mathematical foundation is that these operators satisfy and extend the Gauss divergence theorem. Okay, and in this case we have weighted matrices which are diagonal, so that we have an induced norm because this is a generalizing our products, and this one is the boundary operator. The boundaries appear here when you apply boundary conditions, and this, by the way, which is I don't make that. Usually don't talk that much about this. Those are numerical quadratures. Okay, you can use those to integrate numerically. And we have compared those with Newton codes because in the second order, it coincides with the Newton code scheme, but that's only at the second order. We actually demonstrated, I guess, that there are really bona fide quadratures. You took the Euler expansion that they use for constructing quadratures, satisfy that, produce error and all that jazz. But also an important detail is that all the coefficients are positive. Okay, all the entrants of that matrices, that means that it guarantees positivity of the solution. What do I mean by that? If the solution your problem is negative, it's going to be negative. If there is positive, it won't change. You look at Newton codes, for example, if some of the quadratures have negative numbers and other positive, so it doesn't guarantee there is positive. Okay, as I said before, they're constructed in staggered grids, and that's the reason why for us it makes sense. For example, you're going to solve the wave equation to make it into a first order system because we use a staggered approach, and the scalars are in the center of the cell, and the vectors are in this case coincide with the nodes, but actually in 3D is better. So we got the faces, the faces and the center of the volume. Okay, so this is a little commercial. So we published this book, which actually have not just all the basic information on how to construct the operator that you like. Here is a copy. You're welcome to peruse it, but also has case studies in different applications that we have. After that, we have done quite a bit more. Okay, so all the stuff that we did at the beginning, we construct this in 1D, but it's actually straightforward to get these operators to second order and third order using Kronecker. I discovered that after I did by hand, I wrote by hand the matrices. That's when I discovered that there actually were Kronecker products in there, and that was actually very good.
Can I say something that I saw when I went to your office a few years ago?
Sure.
You had this huge piece of paper with a lot of numbers in the huge piece of paper with all the coefficients of this, just like big matrices, all by hand. So you discovered all things could actually be.
Well, because from 1D to 2D, I mean, at least for me, it wasn't easy to visualize that. So I wrote the 2D in those giant pieces of paper. So I said, okay, by following the lexicographical order in the mesh. You say, okay, here is this, what are the things that give me the divergence, the gradient that I want. And then when you look at the whole matrix, you realize, hey, this is a Kronecker product. Okay, so and the formulas are here, and that's very easy. So for 2 and 3D operators. Okay, so what other thing is actually important that as contributions that we do? Generalmente, when people do the curl, they use stock theorem. And it did turn out that when you use stock theorem, you actually have to do interpolation because of where the operators are defined. So we actually constructed, we have a way to construct the curl, which doesn't involve interpolation, and it's by using divergence, the divergence operator basically is Gauss theorem instead of the stock theorem. Okay, now coming back to MOL, which is what I want to talk about, basically it's very friendly, very easy to use, very flexible, and allows you to solve partial differential equation using the mimetic method. It's not like MATLAB, but in some sense you can think like MATLAB because you can say, okay, I want to solve this. You have the divergence, the gradient, and the curve. So you put your stuff there, you write your equation, and they're just function calls. You say, I want to use the second order, fourth order, sixth order, and you put together your problem. I want to use this boundary condition. We have an operator that you specify the boundary condition here.
So you're only talking about space. You're not talking about time here.
Yes. Vector calculus is in space. We'll get there. Okay. A second. Okay, it's available in C++ and MATLAB. Okay. All functions in MOL return the sparse metric representation. Very efficient. Okay. So the dependence that we have is a library called Armadillo. That is an open source linear algebra. And it's implemented also in C++ and provides the support for the operation with the large sparse matrices. We're talking huge. We solve problems of millions and millions or tens of millions of cells. But because of the representation is the sparse way, we are able to do it very fast. And that's where MATLAB has a problem because MATLAB is basically to do prototyping. So when you want to do something big, then you go to a real language, and then we use C++. So we are one of the things that we're adding, and this is I was going to mention that later, but before Ricardo asks, we actually are working in a Octave version, which is we already have a GPU wrapper that allows you to use using CUDA. You can actually use the library. Now you can use it with Mac, with a Macintosh. You can actually install the library and run it. And also, we are starting to look into having a wrapper, a Python wrapper, and a Fortran wrapper, those two. So the way that if you are a Fortran programmer, you like Fortran programming Fortran, you can actually use a wrapper and use the library. So that's that will, let's say, increase the users, I hope. Okay, so these are a few snippets of what you get when you try. This is a 1D Poisson problem. And you can see here, basically, we have the only operator that we have that is no first order is the Laplacian. Okay? But that you can, instead of multiplying, we already have the Laplacian there. But it really is just a little faster. And here are these, for example, Robin boundary conditions. I mean, they tell you what for example, in this case, this is an operator over 6. Then you have the minimum number of cells that you need to use to be able to use the operators. And then the spacing in the step size, the operator that you want, in this case, a Laplacian, These are the boundary conditions, and you want a staggered grid, so then it gives you a staggered grid.
So if I want to use that Laplacian here, I will, it's sparse matrix, and I just will have to multiply that sparse matrix times the solution to get the Laplacian of the function.
Yeah. For example, like if you want the divergence of a vector, you put your vector and call the function the set divergence, and it gives you the divergence of that. That's the basic functions. Then you combine that to solve PDEs.
Yeah, but here you're not feeding the function that you want to take the Laplacian of. You're constructing a matrix that then later you're going to multiply by you.
Yes. Okay, so, no, but then in this case, you want to solve the system of equations. You got the Laplacian, you got the unknown, and the right-hand side something that you there. And then, okay, so give me the solution.
Well, depending on what you want to do, sometimes you don't want to do this. If you want to integrate, you just need the Laplacian.
Then you can have it. You can have it. You can say, here is my function. I want to multiply. I want the Laplacian of this function. You can have it too. Not a problem. Okay. So here is another one. This is a 1D heat problem. But it's basically the same. The same. What I'm trying to emphasize here is that if you use MATLAB, let's say, and you want to program all these operators, it will, which you can do. It will be a huge number of lines. If you program the operator, as you call, and also if you call MATLAB, it's not going to give you the Laplacian staggered mesh.
My Laplacian in MATLAB is 3 lines. Okay. 1D, I mean 6 lines.
So the next one is, like I said, it was a parabolic problem. It's explicit in this case. And then here you plot and you do whatever. So it's extra. If you just want the Laplacian, it's one line. But if you want to solve and get the answer and plot, that's a few more lines. Okay. So, well, I guess I mentioned this. At the end, you solve a linear system. And if, in this particular case, was time was used, I think it was earlier? Backward earlier? Or what? It was an implicit scheme. Okay, so boundary conditions, if you ask, for example, in this case, well, basically, you got Dirichlet, Neumann, and Robin, and we have an operator that you call, and you say, okay, if you put k equals 0, you write it like alpha u plus beta derivative of u with respect to the normal equal to gamma, and then you pick the parameters. If you want Robin, you choose, and you want Neumann, you choose, and you want Dirichlet, the same. Okay, so a couple of examples. This is an example that is actually innocent, but it's not that easy to solve, even though people say, hey, so what? This is a trivial problem. No, it has a boundary layer. You can make it really hard. And so, but this is a legacy problem from a long time ago, but I came up with this for a class. Okay, so the solution, we know the solution in this case, and using 5 cells, this is the solution. And I compared this. You compare this problem with find a different. I compare it with the support operator method, and we get 1 order of magnitude better. That's the solution. So I think that's okay. So then another example here. This one is a little bit more complicated. It has a full tensor, even though the problem is not that hard. And this was taken from a paper of people who are well known and well appraised and well whatever in the literature. I don't know if you can read the whole thing there. So, but when we look at our example and theirs, hey, we also got another magnitude better. That's our solution. I attribute that to the flux because yes.
But you're comparing same order, same order.
Of course.
No, yeah, because if you're using a higher order, then
Please, Ricardo.
I'm just checking if you're dotting your I's and crossing the T's.
No. Okay. So I'm going to go over, this is a little tedious, for the experts, but this is something where you're asking about temporal discretization. So, but basically here, this is for a wave equation. But here we got the stress, okay, in time, and then we have the velocity. So we're going to use a staggered approach in time and staggering space. So basically, what you get here is the velocity, the projection, I guess, of the velocity on the mesh. And here you write the velocity at n plus a half, which is time, is the velocity of n minus a half, because it's staggered skip 1, is equal to this multiplied by the sum. This is the gradient of the stresses. And stresses is the previous one, and this n is also time. And look at this one goes from n to n plus 1, and the other one from n minus a half to n plus a half. And this is the divergence of the velocities.
This is second order in time.
Just wait. Okay. It is second order. But I'm just explaining how, if you're talking to the students in a classroom, you tell them what is the approach to do this. Now, in use the library, you have to do any of this. Okay? So then you put together the collect like terms and all that jazz, and then you get a Laplacian appear here, and then here is the final result. Now you got here, you're advancing the velocity, we're advancing the stresses, and this matrix here times the previous data. Why do I do it like that? Because it looks nice. Very compact, elegant. Okay.
The stresses is an auxiliary function that you define, or it's part of the problem.
Let me go back one second. This is when you look at there are formulations of wave where they talk a stress formulation and different things. So it's part of the problem. Okay. I didn't come up with any. But this is a little example here. So in this case, we have first order system. We have used the velocity and increased the pressure. We have the initial condition, and the boundary condition is a solid wall. Then this is -1. Very simple problem. But in this case, we compare this with. I don't see this now.
Do you have a figure of
A movie, but I don't see the thing here.
So you had it in a Google Doc?
It's in the.
Okay, good. Okay, let's go back to the. I can download it and then we can see it. But I don't know if it's working.
That's okay. That's okay. Let me see if the same thing is going to happen. I'm going to skip example 1 and 2. Okay. So I should have used my laptop. So that's it.
What is the constitutive law for this material? Is it an isotropic material?
Yeah, this is a very trivial problem. The only reason to do this is because there are 4 methods implemented here, and the only one who brings home the bacon is the mimetic method. The other ones.
But it's a 1D.
Yeah. We do 3D, but like I said, this is for the purpose of illustration. Okay. So I'm gonna skip this also. Okay, this is Berger's equation. We're gonna have the same problem because it was part of that. So in the example, basically, there are 3 methods. Is the last Wendrow, upwing, and the mimetic 2D with second order in time and second order in space. And the last Wendrow doesn't cut it. The upwing works, but the mimetic is the only one who keep the peak of the curve till the shock. So if we combine this with a shock capturing scheme, then it gives you just right where the shock is still the solution Yeah.
So you avoid the Gibbs phenomenon at the boundary of the oscillations.
Yeah. Okay, so non-uniform. Basically, in this case, we're looking at non-uniform meshes, but in a structured mesh. Okay. So basically, what we do is, well, there are two ways to do this. One, you compute the new coefficients when the mesh change, or you modify or you keep the coefficients and modify something else. Okay. Now, in that case, we use what we call reference cells, and basically, this is something important here with the P and the Q that play a role in the boundary operator. Here, for example, we get that the boundary is the product of this wave matrix by the divergence plus the wave matrix of the gradient transpose. And that gives you the boundary operator. But so if you look at second order non-uniform operator, basically the multiplication here is the Jacobian of the cell where you're doing the calculation. And these are the coefficients. So we don't change the coefficients, we compute the Jacobian. For the divergence, it's the same, but it's in the Jacobian is in a different location. Okay, so this is actually was a nice realization that you take, for example, the Q or the wave matrix of the non-uniform is the uniform multiplied by the inverse of the Jacobian of the divergence, which is a corresponding. Yes.
Just non-uniformity of the geometry is the problem, or is it?
No, it's non-uniform mesh in a structured mesh.
Structured mesh.
Yes.
So is the mesh non-uniform in space?
Yes, it is.
So it's not necessarily non-uniformity of.
No, the mesh is non-uniform. The mesh is non-uniform. Okay. So, and the same thing happened with the other the wave matrix. Non-uniform is equal to the uniform weight multiplied by the inverse of the Jacobian of the gradient in the corresponding place. And because of that, it turned out that the boundary operator in a non-uniform mesh is actually the same one than the uniform. That's actually great news. We don't have this. We can use the same.
That will not be.
I know you don't believe it. But.
No, I'm surprised because that's a big advantage from using finite difference. In finite difference, you'll have to modify stuff. Here, you don't have to modify stuff at the boundary because the self-consistent approach of your operator.
Okay, so this is a very simple problem. Okay. So, okay, Ricardo, here is the equation that you want to solve, right? In the continuum. Here is the equation by Woodson. That's a discrete analog of that one. So, and these are the boundary conditions. This was the original, the boundary conditions. So we write it like this. And then this is the system of equation that we solve at the end, which in this case is linear. So
you mount the boundary conditions within your problem.
It is incorporated. And that's actually pretty good because you don't have to do anything strange.
But that doesn't give you an overhead.
No.
Because sometimes
it's
solving both of things at the same time gives you an overhead but here because the boundaries are treated the same way, then everything can be conglomerated. Yeah, I get it.
Yeah. Okay, in this case, for example, we did solution adaptation. So mean using this criteria for the mesh function, this is something that Ricardo knows from his past. It's basically to concentrate the points when there is more changes in the gradient. So we got just even in two adaptations, we get that the solution is really getting pretty fast. And more important, we use second order operators, and then with the adapted, you already get second order. And if we use fourth order operators with the adaptation, we also get fourth order.
So what you're showing us here is that by the adaptation that is not natural for your mimetics, still putting the adaptation doesn't dilute your order.
And it goes fast, actually. Okay, and this is something that I'm gonna start mentioning all the time and even in the papers. We usually use L2 norm, but the natural norm here is not the L2 norm, because we do have a norm that is induced by that inner product. Okay, so we have that norm is the 2 bars. Instead of have here, it has a Q. It's a weighted inner product. Now, of course, this is a finite dimensional space. All the norms are equivalent, but sometimes one is better than others, you know, to do an approximation or estimations. So the first time that we did that was one of my students, Anand. He actually, I told him, use this instead of the L2. And there was not that much difference, but I think it's better to be in the right place. Okay, here is another problem for a 2D boundary layer. And here we're going to have the same problem of the movie. So, but this is the numerical solution, the first iteration. And this is, I think, as the fourth iteration. The true solution and the adapted solution are basically the same. Very, very, very close. Okay. Now let's see if with this one will fly, because I'm going to click a movie. So I hope that soon. But in this, one of the things talking about complicated problems, this is leading in that direction. This is in 2D, but it says a hole in a channel, or would be a missile going through somewhere. So, and the thing is that it's in a irregular geometry. So in this case, we use what is called overlapping grids. And basically, you do overlap all these and do some interpolation point from the Cartesian, which are the green point here. But the boundary conditions do not change. The boundary condition, physical boundary condition is the same. And the advantage of this is that you're able to solve the problem in a Cartesian measure. And so that is way fast, or let's say faster than trying to do something else. Okay, here is a computer solution. Of course, this problem is not that difficult, but it has that hole in there. And what is important to me is that we actually get fourth order in the solution.
So again, as before, you are showing here that by coupling meshes on very different spaces and with interpolation, you're still not degrading your order. So that means that are you doing something very special with the interpolation, or is it just linear between the points, or cubic splines?
You use the same order. In this particular case, I believe that he used third order.
Right, so you need to match at least interpolation,
Yeah.
otherwise there will be degradation.
Oh yeah, but in this one with third order it works because the problem is not that hard. But sometimes, for example, if there is discontinuity or rough coefficients which are not smooth, then you have to send the same one.
The method here is fourth order, but the interpolation is 3, and still you have no degradation.
Yeah, but it was an easy.
Yeah.
If you do, I don't have the other one, but we did one where it was anisotropy, and there was almost a singularity, not quite, but it was sharp, and we were able to get third, which is actually pretty good. I mean, if you using fourth order and you get third order approximation with your scheme in a problem that is not smooth, that's pretty good. And that was published in the Computer Fluids.
So, I mean, from the illustration for this problem, the grids, it looked like the revolution, the Cartesian grid was way lower than the revolution of the annular grid. Is that the case? You still got?
Yes. Well, I mean,
or is this just a schematic?
Yes, and this is also MATLAB.
So he's using shading interpolated MATLAB. So he's just for the plot, it's interpolated. You don't see the grid there because
Right. But I'm just
it's
like
just
in the
plotting
last,
interpolation.
you're looking for the values of whatever this function is,
Yeah.
the solution, at every point on that annular grid. And you're getting that by interpolating from what looks like a much lower resolution.
Well, look at this. The region is this. Right. So, but if you look, we use this. Okay, so this is a cut. So to illustrate the point. So basically, it's all over this. This is true. In this particular case, I will have to double check, but it is the Cartesian is coarser than the other one because you really don't want to compute it here that much. You want to compute in this one.
So are the boundary conditions computed on the faces of those, just on the faces of those elements? Like
The boundary conditions are the real ones. So they're the black one. Yeah.
But how do you compute that on the Cartesian grid? I mean, that doesn't line on the face of a grid. Is that making any sense?
No. Well, I mean, maybe I don't understand what you said. So basically, you
take a boundary conditions on the black or the red dot.
Yeah.
Those don't correspond to points on the faces of your Cartesian.
yes.
I guess I just don't understand.
No, they don't. Otherwise, we don't need it. So, but that's why you do the interpolation to be able to move the solution across. So you compute in the places intermediate, and then you carry the solution across with the interpolation.
Many problems, I just don't understand how. I mean, the boundary conditions and the problems I said, they're imposed on faces, right, of the grid. And the scalar components,
The scalars are in the center, in the centers of the cells.
but I just see red and black dots there that are far away from.
Well, the red are the interpolation points.
Okay.
Red and black are on the annulus. Right. And then you interpolate those into the grid, into the blue grid.
It really works, by the way. So,
I believe it, I just don't understand.
We need to understand how it works.
Okay,
That it
well-
works. We understand that it works. We don't know how it works.
okay, so now this actually is the latest addition. This is, like I said before, we are, I consider mole to be a building block for constructed high order, it could be second, but high performance codes. I mean, really robust codes for doing modeling and simulation. This is actually Navier-Stokes 2D, and this is a standard problem so that everybody does, but it worked well. And this is, for example, since you guys are going to be in Access, I believe that there's going to be, this is a Jarrod, which is my student who did this. He, using the mole, now has a 3D, and we're building a GCCOM, a new GCCOM in 3D that is using mole as a building block. Okay, the second one is the Seamount. In this case, you got okay, so you go like this is a cross section, but it's in 3D. And it gets the physics. So that's the other part.
This is laminar flow of the whole.
Well, this is water. This is a, you call it underground seamount. You know, there is the current coming through here. And then, yes, and then the important thing is that in the part here start.
It's not really laminar because
Yeah.
you already get this about this.
Okay, so one aspect that is very important is the stability and the performance. And like I said, as Ricardo mentioned, currently Mimetic operator provides specialist. So what are we doing? Time-dependent problem. We use, I don't like to call it like this, but I have no choice. Mimetic leapfrog, because it's the problem is you say leapfrog, people think about finite difference. But we use the stagger the same way that the leapfrog, and it works, and it is mimetic. It actually conserves energy, everything, stable, all that. If you want second order, you just use second order mimetic and the leapfrog, and that hard to beat. Okay? Now, of course, if you want problem higher order, then the other we use a Runga-Kutta, for example, for the GCCOM, which is a non-hydrostatic coastal ocean model. We use Runga-Kutta 3 actually. Now, we also use the I think it's a strongly preserving something. But recently we started, we implemented something which is called relaxation Runga-Kutta. That was developed by David Ketchison, who was a student of Randy Lebec, I think. And I've known him for a long time, and we talk every conference, and I've run into him 3 years ago, I guess, in Valencia, Spain. And he said, he told me, I got it. And then he sent me a paper, we implemented, and it worked. So we actually have how do you call it? We implemented this relaxation Runga-Kutta, which you use a parameter to control the conservation of energy. And we have, actually, we just got a paper accepted where we did a few examples, because that's never been done with mimetics. And we got to conserve energy to machine precision. So, and what we're going to do next is to compare with symplectic methods. For example, like if you have a Hamiltonian structure, nobody, I think, would beat a symplectic integration. We use Newton-Verlet, and we use Forest root, which is a fourth order, second and fourth order. And we're going to compare the two, but I think it'll be very hard. This one is natural. It's globally stable and everything, and conserve energy. But if you don't have a Hamiltonian structure in your problem, you have to do something else. Sometimes you're lucky and you can actually decouple. We did one in a previous paper where we did I think it was an acoustic problem, wave in 3D, and we actually did I guess, rewrote it in a way that it was uncoupled, decoupled into problem with Hamiltonian structure, and then we use Forest root and great. So, okay, so this is, I like this picture because you got the spatial discretization, time discretization, but also you have to keep into account the interpolation because the operators live in different places. Okay, okay, so what is the take-home message here? We can do, even though I didn't show you an example, we actually implemented now in MOL the operators in curvilinear coordinates. Okay? So we have mimetic curvilinear coordinate operators, and that's what we're using in the GCCOM. So, and we also we are adding the time integration as part of MOL. So we have a lot of examples, but they're not part of the library. It's just to illustrate, but we're going to incorporate a few time integration. One is the leapfrog, mimetic leapfrog, and the relaxation Runga-Kutta, and also the symplectic one that will be part of the toolbox, like you want to call it that way. So when you don't have to program it yourself. So I will, this is ongoing work. They were already in my lab, and C++ is supposed to be done today, but Johnny didn't show up because he hasn't finished it, I guess. And then we are optimization and parallelization of some part of the library, and tailoring some time integrators as part of the library, not just as examples, and stability analysis in different problems. And there is still a way open thing for here, even in bioengineering or how to call it, Einstein condensates and all the stuff that you do. So
Mathematical physics.
okay, mathematical physics. Okay, so I will acknowledge with some
Losses.
well,
You give them
I don't want to make the mistake, and you probably remember that Barack Obama was given the Nobel Prize before he didn't do anything. He did anything. And because they gave it to him, he didn't do anything. So I don't want to give too much credit till the thing happened. Okay? On that note, thank you very much for your time.
Thank you.
Any questions?
Is there a nice way to handle a sort of series of nested domains? So properties are well defined within each domain, but then you have boundaries, another boundary.
So different problems on different grids that they are overlapping in the boundaries.
I'm actually thinking, so
The head,
a typical kind of head model would be is you start with a scalp, and then there's a scalp layer. You might treat that as a domain. And then inside that is a skull. And then inside that it would be a thin layer of sort of the spinal fluid, and then within that is the brain itself. So you have this nested structure, and sometimes you just treat the boundaries of those brain boundary through the spinal fluid with the skull, the boundary of one with fluid with the skull with the skin layer, and then the skin with the hair.
I would say yes, and this is, but we need at least one undergrad to start that one.
So you have not applied mimetic operators to different domains with different physics and couple them to the boundary?
Yeah, we do also have we do have something that we call the DCT, which is Distributed Coupling Toolkit, that allows you to actually couple distributed coupling, different modules, different models, different codes, with different concurrently with different time step, different space step, and all that jazz. And actually, Jarrod, for his master thesis, he coupled the GCCOM with something called SWASH, which is a surface code. And he got it to work great. We tested, we got very good results. And then I asked him, okay, yeah, but can you solve the problem with your package now and beat SWASH? And he did it, and he got a paper. So it is possible, and we need, how do you call it, to work a little more on that coupling, because at least Jarrod complaint was that it's very hard to use. So now we're trying to make it more friendly. And I don't know if you're familiar with something called MCT. You may be. No? Okay, in atmospheric science, there is a big code that everybody uses, and they use called MCT. I think it's Master Toolkit, but in those type of codes, in that approach, that you have to wait till that's a typical problem. You couple different models, and you have to wait till one finish to start the other one. In this one, this MCT was creating a bottleneck because they've sent threads to different places and they wait. In the DCT, it keep going in a distributed way, and it's getting information as it marches. We published that paper, and we haven't done that much until now that we discovered that the MCT has incorporated some of the stuff that we put in there. So, good for them. Yes.
So you're developing mimetic operators for curvilinear geometries. Is it possible to transform them for arbitrary grid geometries? I mean, I think this relates to the problem he's bringing up. In Asia, you have a lot of things that just,
well,
cylinders there, they're just
it depends. I think we talk about hexahedral meshes. Depends what it is. Now, I still don't have a student who's interested in expanded the methods to unstructured meshes, which is a different. That's
yeah,
what,
that's
yes.
sort of what I'm asking.
Yes.
I don't know enough about
But I do have two ways to solve problems in structural meshes. One is curvilinear operators, and the other the overlapping grid. If I can do that without having to, by the way, using unstructured meshes bring other problems.
Yeah,
They're very easy. They're very easy to generate those meshes, but then it brings all. But if you can live in the Cartesian, I do like a Cartan. If you live in the Cartesian world, you can compute everything in the Cartesian world and move around to the geometry of the physics and satisfy the physics. That's unbearable.
I mean, I guess what I'm asking philosophically, can you preserve these nice properties in terms of, say, natural conservation if you try to transform?
Yeah, I have no idea. I took a student long time ago. He worked in this for a while and then he left. So he didn't continue the program. I would love to get another student or somebody who's interested in this.
You can get unstructured grids, oddball things like the brain by having triangles. It's just a triangle.
Yeah.
So.
Of course, when you do triangles, then you lose accuracy. That's a
question.
Yes, I have a question regarding the time integration. So in Discretization, what we often do is we use different time integration, different time discretization for different terms. And do you do the same thing, or you just?
I have never, I don't have any problem doing that, but I have never worked in a problem that I have to do that.
I see. And also, does the time integration scheme satisfy integration by parts?
Yes.
Even the range quota.
Oh, I'm sorry. The Mimetic certified integration by parts. The other one, I don't know. I know that the standard Runge-Kutta doesn't conserve energy. That much I know. But I don't know about integration by parts.
So if you take two triangles, you can almost construct an odd-shaped rectangle.
Yes.
So you have.
And that's what people, a lot of people do.
That's all.
Okay. Anybody in the over zone? How do you call the?
I mean, I can check the chat too.
Yeah, will you please do that? So.
Oh, if you.
And also, people are welcome to unmute.
I don't know if they know that.
If you do Octave, it's really annoying to install.
I'm not gonna do it.
Well,
whoever
no.
wants to, then they can use.
Yeah, I'm just telling you that it's Octave is.
The reason I mentioned this is because we have a reviewer who complained that it wasn't working okay. And by the way, well, it didn't work for him was the plotting, which was, we use MATLAB, the plot from MATLAB.
No questions.
I think that they're gone.
All right, any other questions? Not, I would like you to thank the speaker for two reasons, because of the talk and because today is his birthday. So, thank you.